So everything we did with z-scores in chapter 2.5 comes back with the normal distribution, but we're going to extend that capability with looking at percentages in general. And so what we have to do is we have to get some orientation here into what we want to do. And so when we look at a normal curve, what we know for sure, because this is the mean, median, and mode, well, in the definition of the median, half of the stuff is on this side and half of the stuff is on this side. So 50% of the probability is on either side. So that means even though this goes off to infinity this way, if I work my way from infinity to this point, I have a 50% chance of grabbing stuff. And if I work my way from here all the way out to infinity, there's another 50% chance. And so the amount of stuff divides around that 50% line. And so what we end up wanting to do is we want to find probabilities. And there's kind of two ways that this is done. Back in the day, they used to publish tables, and we'd look in the table to find out what the probability is. But the thing is, with these probabilities, is that they're based off of areas. And so we have the option of the probability of everything up to this number, or the probability of everything after the number. And most of our technology and most of the way we'll do this is we'll be doing the cumulative probability, going from 0 up until the point that defines our boundary. And we'll get the probability up to that. And we'll get the area underneath the curve. So what we tend to want to do is we want to find a way of calculating that. So for example, if I have to do a distribution that has a mean of 500 and a standard deviation of 100, and I want to find the probability of my variable being less than 600. And so that's what is the chance that that will be less than 600. That corresponds to the amount of stuff of the area underneath the curve up to 600. And so this area is this probability of x less than 600. And so what we want to do is we want to think about what that means. Well, my standard deviation is 100. So from here to here is plus 1 standard deviation. And so that means the z-score would equal 1. And so the 600 has a z-score of 1. And so we want to find the area underneath the curve up to a z-score of 1. Well, we already know, right, that if we go back to our empirical rule, that was approximately plus 34%, right? And so 50 plus 34, well, that's a probability of 0.84. So the probability of x being less than 600 is about the probability of 0.84. And that's what our empirical rule did for us. But not all standard deviations are these nice, not all z-scores are these nice 1 standard deviation, 2 standard deviations. And so we might get a different way of looking at it. So let's look at an example here. So we get a study finds that on average, college students with jobs worked a mean of 22 hours per week. And the standard deviation of this was 9 hours. And so we want to find the probability that some college student works less than 4 hours per week. So our mean is 9 hours. And what I tend to do is I draw my normal curve, and then I go, well, somewhere over here is going to be 4 hours. I need to find the z-score with that and the probability that comes with it. But I like knowing which side that I am with the mean, because over here I have negative z-scores and over here I have positive z-scores. And I also have to realize negative z-scores deal with the probabilities from 0 to 50%, while positive z-scores are from 50 to 100%, which is 1.0. Remember, I've always said I say decimals as percentages. And so just putting a dot on here and going, well, you know what? I'm looking for the area of the curve here. I don't know what the z-score is yet, but that's going to be the first thing I find. And so the z-scores are going to be our link. And so what we do is we go, well, the z is equal to x minus mu, right? X minus the mean divided by the standard deviation, which is 4 minus 22. Whoops, I put 9 hours. That's the standard deviation. It was 22. Right? You're all probably shouting at me watching the video. Easy fix. And so 4 minus 22, that's negative 2 standard deviations. And so if we look on a table or we pull up less than negative 2 standard deviations, the probability that someone works less than 4 hours corresponds to a z-score of negative 2 or about 0.0228. Right? I think we estimated it as being 0.225 in the empirical rule. But once we plug this in technology, we'll see that's the number. And so this is an unusual event. Unusual, right? It's not very unusual. It's unusual across. All right, let's look at another way we can view this. And we'll look at a range. And so supermarkets are common. They'll do a lot of trips in the supermarket. This is a typical, supermarkets are common. Supermarkets analytics are a common thing to look at. One of the things that you'll see is a survey, why this particular example, finds a shopper spends an average of 43 minutes in a store. And so if you know this with a standard deviation of 12 minutes, you know how to charge for advertising repeats, right? You'd probably want to repeat somewhere within a half hour. That would guarantee that you hit the most people. And as a supermarket, they would want to look at, like, well, how do you play for advertising on, like, the PA system, or, you know, how should you staff? There's many different things that this type of probability and knowledge will do. And so what we want to do is we want to find out what's the probability that the shoppers will be between 22 and 52 minutes. Or we'll do that for part A. We want to find between 22 or 52 minutes. But we only can do less than values, right? The charts, tables, everything we did about area of the curve was to the right. So I want to put my 43 here. And I'm going to say, well, 52 is going to be over here. And 22 is over here somewhere. Now, what I want to think about is, I'm going to lightly color in the area of the curve that we'd get if I just looked at the z-score for 52. If I just looked at the z-score for 52, I'd get the area under the curve to here. And if I just looked at the z-score for 22, I would get the area here. Well, notice the green cancels out the red, or I've subtracted out a bit. And subtraction ends up being our key, because this is equal to, it's exactly the same as the probability of x being less than 52 minus the probability of x being less than 22. And so these intervals like this, we write like this. And so to find the chance of the probability of being within two particular ranges, I need to find the z's for these two ends. So we'll say this, I usually call this my z2s and these my z1s, right? The first one and the second one. And then in my z-score, z1 is 22 minus 43 over 12, which is a negative 1.75. And z2 is 52 minus 43 over 12, which is 0.75. And what we want to do is we want to convert that z-score into a probability. All right, well, I haven't done that yet. And so what we're going to do here is we're going to convert these z-scores into a probability using a table. And so I'm going to pull up the book here and go into the table in the book for z-scores so that we can see how we pull these together. So let me get this open here. You'll hear me type for a second. Into our book. Into our table. And you'll find even with technology, this is probably the common way people talk about z-scores and use them are tables. And it's one of the few tools I still see with people that use statistics. They'll pull out tables. Because once you get this number, it's really easy to get this number, I should say. And so just looking it up in a table is the easiest way. So let me make sure. It's not showing. Oh, there it was. I just clicked on the wrong thing. That's why. There we go. And so in the table of contents, I'm going to go to tables. And then in here's a standard normal distribution. And so our z-score for the negative 1.75. And so what I want to do is I want to build the number negative 1.75. And so I come down here, and here's negative 1.7, and I need to get the 5, which is down this column. So I come across here until I get under 5, and it's telling me the percentage of everything up to a z-score of negative 1.75 is 4%, right? Or 0.0401 is the probability. So I'm going to come back to my chart here, and I'm going to say, okay, so the probability of being less than 22, because that corresponds with the negative 1.75, is 0.0401 from the table. Okay, I'm going to go back over to the table here. And now I'm going to have to go forward a page. And here's our positive z-scores. So notice the positive ones are here. And my z-score for z2 was 0.75. And so what I want to do is I want to get to 0.75. So I come to 0.7 and over to 5. And that's 0.7734. Come back here. And the probability of x being less than 52 was 0.7734. And so using this relationship, finding the area between the curve by subtracting the two, I find that the probability of a shopper spending between 22 and 52 minutes in a store based off of the survey results is I subtract these two, and its probability is 0.7333, or 73.33%. And so that's the chances that they'll be in the store in that period of time. And so notice that we can get the scores to the right, and so if we have a less than, we get the probability directly. If we have in between two, we have to subtract. And so now we want to look at the other option, which what is the probability that they spend more than 37 minutes? So again, I'll go back to my graph. That was 43, so 37 is over here. Well, the probability that I'm looking for is this. But the one I can calculate is this. But what I can do is I can say, and I can go back to the idea of the complement that we used in probability space. If I can calculate this, but I want the thing on the other side, I want its complement. So the probability that the variable is less than 37 minutes is going to be the same as 1 minus, I'm sorry, greater than 37. The variable being less than 37 is kind of leading up to this, right? And so complements come into play here. If we need the right side, we take the complement of the left side. And so we're going to do the same thing. We're going to find the z-score. So the z of this is 37 minus 43 over, what was our standard deviation, 12. And let's see here, that is negative 0.5. So what I'm going to do is I'm going to come back, whoops, there we go, and I want to find the negative 0.75. So I'll go to the table for negative 0.7 and over to 5, and it's 0.22, no, I'm off here, negative 7, did I mess up my z-score? Oops, yeah, I did mess up my z-score. This is what I get for running. It was, I'm saying 7.5, but I wrote it down right. It's negative 0.5. Sorry. Just a little bit of verbal weirdness today, I guess. Such is life. Which will be nice to show on the chart because 0 is in a weird place. So down at the bottom here, and this chart continues down, I come down for negative 0.5, but I need the last digit to be 0. So if I come over here, this is where the last digit is 0. I come down here, and that's 0.3085. So let's come back here. And so the probability associated with x being less than 37 is 0.3085, and so the probability I want, I'm going to subtract, and that gives me 0.6915. So notice how using the idea of the complement and using the difference between boundaries help us calculate our probabilities with z-scores. And that helps us work our way through. Now, Excel is really nice. Excel has a function for this, which we'll explore in more, which is similar to the binomial distribution. It's the normal distribution. And then you want your x value. So in this case, it would be 37. Then it wants our mean, which would be 43. Notice the commas. Then the standard deviation. And then we want it to be cumulative. So the cumulative will be true. And this will give me everything up to 37. And so what I want to do when I do that formula is 1 minus. And we'll play with this more in technology, but our technology gives us the ability to calculate this for us. And this is how we find percentages. We can have values in our data, and we can find the percentage of how much stuff is within certain areas. And that's really where this empirical rule came from. Now, there is a mathematical function that drives the shape of this curve. It's actually not easy to calculate. I don't even show the mathematics for it. It's e to the negative, what is it, mu, or x minus mu over sigma squared, right, is kind of how the function works. And there's 1 over the square root of 2 pi in the front of it, right? So it's a really weird calculation. I think there's also a sigma out front. And that's why there's tables for these. This was so hard to calculate that mathematicians for about 100 years would build tables of these. And we'll play with the tables more, and we'll also play with our technology. But this kind of wraps our way through section 2 in chapter 5. I'm going to work into how we go backwards, how we find values from percentages. And we're going to do a little back and forth with this.